Welcome to the second session of the ARM64 Assembly Language and Architecture tutorial. In this part, we're going to cover the arithmetic instructions, and we will code addition, subtraction, multiplication, and division programs. Floating point and vectors are deferred until a later tutorial. We'll also look at shift and rotate instructions, the logic operators such as AND OR, along with exclusive or are shown. Then, bit-twiddling operations such as bitwise bit clear and bit field insert will be demonstrated. This is a fairly involved video, but we will trace the listings using GDB to show each of the program steps. Before we delve into the arithmetic functions, we want to review the data sizes that are available. The color-coded chart shows 4 sections with each section divided into 32 bits. Each color represents a different data size. The least significant bits, 31 through 0, are at the top with the last 32 bits, 127 through 96 shown at the bottom. For arithmetic, the smallest data size that we will deal with are 8-bit bytes, which occupy bits 0 to 7. Next are 16-bit unsigned and signed half words, which take up bits 0 to 15. We'll look at unsigned and unsigned words, which use bits 0 right up to 31. After this, we have 64-bit double words, which span 2 of the chart sections with bits 0 to 31 for the lower half of the word, and bits 32 to 63 for the higher half. Finally, we show quad words, which are 128 bits wide, spanning across all 4 sections. The first instruction that we're going to look at in the arithmetic family will be the add instruction, and we're going to cover various types of additions. We also need to be familiar with a concept known as sign extension, and that will be explained as we go through the programs, but essentially you can think of it like a 4-digit car odometer that is about to roll over from 9999 to 0. This means that 9999 represents -1, since adding 1 to 9999 gives a result of 0. The companion book to this series covers number complements in great detail, but for now assume that the car was upgraded to a 6-digit odometer. Since the value 9999 represented -1 previously, to ensure consistency the upper 2 digits would require extending the 9's value, giving a result of 999999 with a 6-digit resolution. Now in both cases, the number represented is -1, as adding 1 gives a 0 result. The program first seeds some immediate values, and then we perform various addition instructions, with the results in the comments as shown. There are 2 types of extensions, signed and unsigned. The next part of an extended add instruction is to specify the data size. Here we will perform addition on bytes and half words. So the format is signed or unsigned, with the arithmetic function and then the data size. When tracing the program through GDB, we'll be able to follow the progress. Here's a chart summarizing the operations: unsigned extension for bytes, signed extension for bytes, unsigned and signed extensions for half words, and then finally for 32-bit words. You may recall from an earlier session that we talked about the processor state and some of the flags. So these flags are negative, 0, carry, and overflow. Arithmetic instructions can cause any of these conditions to occur. With the add instruction, the flags are not affected, but with the add s instruction, we do affect the state. So there's a big difference. You can try this in different programs once using add s, and then plain add not using it. It's not always necessary to monitor the flags if the numbers are bounded, because if you know that the numbers you're dealing with will not exceed these bounds, and they won't cause these conditions, then there's no need to keep checking for them after every calculation. So this potentially can save time when executing operations. So now we're going to have a look at some of these add s examples where they do affect the flag. So we will again seed a number of registers. We'll perform these add s operations. We'll look at the condition codes after this, And we can also use an instruction called MRS, where we're moving the condition code flags into the X0 register. So we can simply look at the X0 register to see what's happening. So again, you can see that these instructions have got the results shown in the comments. So when we trace this code through GDB, we should be able to see this and we can tell exactly what's going on. So typically, when these instructions are carried out, depending on the result, we may do a branch or jump to a different part of the program to deal with these events. The next instruction that we're going to examine is add with carry. We're going to contrast that with ADC add with carry, ADCS add with carry set, and add on its own. The first task is to load up registers X4 and X5 with full 64-bit values, and we're going to examine how the carry is handled. This is useful for multiple word additions. The first instruction, add with carry set X6, X4, X5, will give a hex result with 15 Fs and 1 E at the end, because it's adding X4 and X5 and the carry bit. Now at this point the carry bit has not been set, so this is the incoming carry bit. After this we're going to put the condition flags into X0 so we can examine them later on if needed. The next instruction, add with carry, will actually use the carry in bit, but it will not, unlike the previous instruction add with carry set, change the condition code flags. So the carry bit will be staying the same as it was beforehand. Again, we're going to save the condition flags in X0. Executing, add with carry will result in an X6 value of 16 Fs, since we are adding in the carry bits. We do not affect or change the condition flags. Finally, the add instruction does not use the carry, so it's going to give us the result of 15 Fs followed by an Rs. Now to summarise, the add with carry uses the carry bit, but it does not update the flags. Add with carry set does use the carry in bit and does update the flags. Add with carry on its own does not use the carry in bit and does not update the flags. An add to S instruction will not use the carry in, but it will set the flags accordingly. Next, we're going to look at some subtraction examples. Subtraction is fairly similar to addition, so we won't spend too much time on this function. However, I do want to talk a little bit about carries and borrows. The same flag is used for carry and borrow. However, inverse polarity is used to signify a borrow condition. So when the carry flag is set, it means that a carry has occurred. But in the borrow case, then if the flag is clear, set to 0, it means that a borrow has occurred from a subtraction operation. So you can see there in the comments. With the subtraction operation, it sets the carry equal to 1 to signify that no borrow occurred, and it sets it to be clear when a borrow condition is true. So this is the opposite from the carry condition, and this is something to be aware of. This is a fairly simple program with two cases. The first case forces a borrow since the register values are set up so that the minuend is smaller than the subtrahend. Here, register W0 is the minuend and register W1 is the subtrahend. Case 2 gives opposite values to registers W0 and W1. Corresponding messages are printed depending on the state of the carry flag. We are going to have a separate tutorial on branching, jumping and loops, but for now the instruction BCC is branch on carry clear. We have already discussed in an earlier video how to set up the registers for printing, but here we can use a small assembler trick to calculate the string length rather than defining it as a static value. The line len_borrow equals dot minus borrow message means take the current address, which now points to the number of characters beyond where borrow message was first defined. So subtracting the start of borrow message from the current location gives the length of the string in bytes as defined by the ASCII directive. The next instruction that we're going to look at is multiplication, and there are many variants of the multiplication instruction. First of all, the MUL instruction is actually an alias of MADD. The idea behind the multiply and add is that it'll take 3 register operands. It will multiply 2 of the registers together, and then after that it will add a third value placing the result in the destination. Sometimes you'll only want to multiply 2 registers on their own and not perform addition. So in this case, then the addition operand will have a value of 0. So the format of the instruction is MADD, XD, XN, XM, and XA. Now you can see in the bit field format down there that the RM register is the second general purpose register which holds the multiplier. The RN register is the general purpose register holding the multiplicand, and then RA is the general purpose register that will be added to the multiply result. So RM and RN are multiplied together. And then optionally, we'll add the third general purpose register RA, putting the result into RD, the destination register. There is also a complementary instruction MSub, and in this case the format is very similar. However, you can actually see that bit 15 is the bit that will indicate whether it's an addition or a subtraction, because it's addition if bit 15 is 0, and then if it's set to 1 it's a subtraction. So we'll look at that in some detail. One of the things that we need to be aware of is that when we multiply these 2 registers together, assuming X registers, they are 64-bit registers, and the destination is also 64 bits wide. So this means you're going to have an incorrect result if you get an overflow condition. Later on, we're going to look at how to multiply 2 64-bit registers together and get a 128-bit result. But for now, if you're sure that your condition is going to be such that 64 bits is plenty and that calculations will never exceed that value, then you're okay. But you need to be aware of this as well. In this next program, we'll look at multiply and addition, and also we combine it with multiply and subtract. So first of all, we start off with the program seeding x0 with the value 1024. Then we seed x1 with the value 60, and we seed x2 with the value 1000. First we'll perform multiply and add. The destination register is x3, and you can see from the comments there that we first of all multiply x1 by x2, so that's going to be 60 times 1000, and then we add x0, which is 1024, and that gives us a result of 61,024, or hex EE60. Next we will execute multiply and subtract. We will use similar operands but in a different order. The instruction is M sub x4, so x4 is our destination register. And we're going to multiply x0 by x1. This result will be subtracted from x3, and that will give us a negative value of minus 416, or in hex with the Fs, followed by E60. So that's the MSub and the MAdd instructions. If we only want to multiply, then we use the MUL alias. MUL aliases to MADD, but it uses the 0 register as the add operand. Of course, if you do not want to use this alias, then simply specify XZR with MADD. Here we're going to look at the unsigned multiply and signed multiply long instructions. Now these instructions multiply 2 32-bit registers together. So make sure you specify W in the instructions. And the destination will be a 64-bit X register. So we're multiplying 2 32-bit numbers, and we're expanding the result into a 64-bit register. If you look at the program listing here, you can see that we're first running unsigned multiply x2, so 64-bit, and then followed by W4 and W5, the 2 32-bit registers. The second instruction is similar, but this time it is signed. So when we perform unsigned multiply, then we'll get the result hex FFFFFFFE0 00000001. And then when we execute the signed version with smul, we'll get a different result of +1. So because we're loading up the registers with all ones, in the case of the signed instruction, that's -1 in each of the registers, so W4 and W5. And we know, of course, that -1 times -1 gives a value of +1. Now if we disassemble umul and smul, we can see then that these are aliased again. So we have unsigned multiply and add long, and signed multiply and add long as well. Here's the bit field breakdown. We have the 32-bit hex instruction here, and you can see here we're using the sign multiply add long instruction. We're putting the result into the x2 register. Our two operands that we're going to multiply together are held in WE4 and W5, and we're using the 0 register, which is the x31 register, because we're not interested in performing an addition or subtraction. So by using this, then it simply breaks down into just nothing more than multiplying two registers together. Now if we look at the bit field breakdown then, bit 31 is the size field, and that's equal to 1, denoting 64 bits. The bits here following signify the type of instruction that we are dealing with. The U field is a single bit field, and that'll either be 1 or 0. So we can see if it's a 0, it means signed, and if it's a 1, it means unsigned. Then if we look at the second source, operand, that's W5. So you can see here 5101. The next thing is this O0 field, and depending on whether this is 0 or 1, it means either addition or subtraction. So between the U bit and the O0 bit, we can uniquely identify these variants: sign multiply add long, sign multiply subtract long, unsigned multiply add long, and unsigned multiply subtract long. So you can see in the case of our signed instruction, the 1 signifies signed, and if set to 0 signifies unsigned. And similarly, here if we have a 0, then it's an addition, and if it's set to a 1, it's a subtraction. So we can tell both of those cases there. The next field we have is the RA, and this is the register that we're going to either add or subtract onto the result. But again, we've specified this to be the XCR register. So in that case, it's register X31. So all the bits are set to be high, which signifies 31. Then we have the first operand register, which is here W4. And then finally, we have the destination register, which is 2. So that's up here. The next program is going to multiply two 64-bit numbers together, which will generate a large 128-bit result. We have already seen that we can multiply two 32-bit W registers together to make a 64-bit number. The instruction has two forms: a 32-bit format with W registers and a 64-bit variant using the X registers. The instruction will be used with X registers to form the lower 64 bits of the result, and the destination register will represent bits 63 through 0. We're going to introduce new instructions to generate the high-order bits: 127 through 64 for the upper half. These instructions are MUL with the letter H appended, signifying high. This instruction multiplies two 64-bit values together, writing bits 127 through 64 of the result to a 64-bit destination register. Now, if you look at the listing, first we will seed the operand registers X4 and X5. And then after we've done that, we'll multiply the value in X4 and the value in X5 using the MUL instruction. So this makes up the lower 64 bits. We'll put the result into X2. And then with the unsigned multiply high instruction, we're going to use the same register, operand pair, and load the result into destination register X3. The combined values of X2 and register X3 give the full 128-bit result. The next instructions that we're going to look at are msub and mneg. Mneg stands for multiply negate, and it's actually an alias of msub. So the format is msub xd xn xm xa. xd is the 64-bit x destination register. xm is the first operand x register. xm is the second operand x register, and xa is the third operand x register. And this will hold the minuend. So the minuend is the number that we're going to subtract the product from. The operation then multiplies xm and xn together. This is the product. And then it subtracts this product from the third operand register, xa. Now if we use mneg, then it's equivalent to using xzr as the third operand. So it will negate the product. This is because instead of simply saying x, a minus the product of x m times xn, it'll simply become 0, minus the product, which is the same thing as minus the product. So this is how it negates the product. If we look at the neg L and neg L, these are the unsigned and signed 32-bit negate instructions. So these instructions multiply two 32-bit W registers. The product is negated and the result is stored in a 64-bit X register. And these are aliases for sub L and sub L respectively. The next operator that we're going to look at is division. Division operations can be either signed or unsigned. And the instructions for this is simply udiv and sdiv. So the format is sdiv or udiv, followed by rd, rn and rm. So here rd is the destination register, rn is the numerator, rm is for the denominator. And the registers can be 32-bit or 64-bit. So we simply use the W or the X prefix that are designated. A couple of things to watch out for. Dividing by 0 will not give you an error. It'll actually return the value 0. So you need to test this separately. You can't just trap on it. Also, there's no provision made for recording the remainder. So there's no such instruction as rem for remainder. You need to calculate this separately in your program. The multiplication instructions are some of the more complex ones that we've met. The idea behind this listing is to capture the majority of the multiplication commands. The comments will show the results that are obtained, and then we'll use GDB to trace the program flow. This should help reinforce our understanding. The division instructions used are quite simple really compared to multiplication. As mentioned though, there are a few caveats to be aware of, such as dividing by 0 and the fact that there's no remainder instruction. Since there is no remainder instruction, it had been simulated in this program with an instruction near the bottom of the listing, m sub x11, x10, x5, x4, and this will actually calculate the remainder. So it's fairly easy to see how this is done. We take the previous results of x10, x4 and x5 and we put the result in x11. So x11 is going to simply hold the remainder for us. Try a few examples by hand to see how it works. So after this brief description, we'll follow up now with the GDB session. And you'll see the registers changing as we go forward. Feel free to pause at this point to see if you agree with the values in the comments. The first action that we need to take is to move some seed values into some of the registers. Previously we used the move keep instruction, and we haven't really used the move n command. But when we're using values where we have the same polarity, it's quite easy to do, and we can do this in one instruction. So here we're going to move into register W4, the number 0, and then we're going to negate all those bits. So what will happen is after we've run this, is that we'll have a value of all ones in W4, and we'll do the same with W5. So hit next. And again, and if you look at W5 and W4, we have these values here. So that's a more economical way to do things. With W6, we're just going to do a regular move since it's a 4 hex digits. Half-word instruction. So now we have our values. The first task is to use the umul instruction. And if you recall, in a previous example, umul used two 32-bit registers as operands. So these are the W registers here. And we'll put the result into a 64-bit X register. We'll hit Next. And the result then is put into X2. So we can look up here, and you can see this is the value you get when we multiply X4 by X5. Remember, these are 32-bit registers, and we're putting them into a 64-bit register. The next instruction is the signed multiply variant of it. So the same instruction, except instead of being unsigned, it's signed. So hit Next. And we now have the value of 1 in X2. And the reason for this is quite simple, because X4 and X5 were all 1s, and in signed arithmetic, that's the value of -1, because adding 1 to this value of all 1s will bring us back to 0 again. So when we multiply -1 by -1, we get +1. And that's the reason for X2 ending up with the number +1. The next action that we want to do is seedback register 4, but this time it's X4 rather than W4. So we're going to have 64 bits of 1s. So here we have X4 with all 1s, and we'll do the same thing for X5. And there it is. The next thing we want to do is to multiply the contents of these two together, and then we're going to subtract it from the value of X6. So we'll do that, and we'll put the result in X7. So X7 is here, FFFE hex, and that's the value we get. So again, this is something you might want to check by hand just to show that you understand the mechanics of the operation. Next, we're going to execute mneg X4 and X5. So again, -1 by -1 gives us +1. Hit Next. And if we look in X8, here's a value of -1. So we negated +1 to -1. Now we're going to run an unsigned multiply of W4 and W5. So we're going to use the smaller bits, put the value into X9. So if we look at that one, here's X9, and we have this value here. So what happens is we multiply them together. We get that value. Then we invert the bits, so all these F's go to zeros. Then we add 1 for 2's complement arithmetic, and that gives us this value. So that's how we obtain this value in X9. Okay, we were going to move on to division. So let's put some different values into X4 and X5. So X4 has now got the value 2000 in it. X5 has now got the value 4. So if we do an unsigned division, straightforward enough, we're going to divide 2000 by 4, and we're going to put the result into X3. So hit Next. And there's X3 now with 500 in it, because 2000 divided by 4 is indeed equal to 500. Now we're going to subtract 1 from the X4 value, so that the number 4 won't divide unequally. So if we do the division now and put the result in X10, we can see we get this value here. So there's some truncation really going on. We did mention that there's no rem instruction, like for a remainder. So we can simulate this by taking the quotients and numerators. And what we'll do is we'll execute this instruction here and put the result in X11. So X11 will contain the remainder. So hit Next. And the remainder is 3, which is correct. So, again, I mentioned earlier, it might be no harm just to walk through the instruction here on paper just so that you understand how the remainder function works, and this is something we might use later on as a macro or function. Next thing we're going to do is seed X5 with a value 0 because we're going to use that to divide. And we know that normally dividing by X5 is illegal. In the case of ARM64 though, if we look at x3, it simply returns a value. So there's no trap interrupt or anything like that. That's all that happens. So, something you might want to check for as well. Don't just assume that you had a remainder of 0. It might be that you're dividing by 0. Alright, let's quit GDB. And we'll move on then to shift and rotate instructions. Now we're going to cover shift and rotate instructions. The table below summarizes everything. First, with the logical shift left instruction, the bits are shifted leftwards in this direction and the vacated bits are filled with zeros. So you can see these bits all get shifted over and these zeros come in. These 3 bits at the end are discarded and they fall into the bit bucket. This is an example of an immediate shift of 3 places. So here we specify that the zeros move in from the left, and we can use either an immediate or register operand. So our example is immediate. Next command that we will look at is the logical shift, right? Instruction, and this shifts bits the opposite way. So data gets shifted across here, and in this case, we're using a register. So the register holds the value 5, which is W0, and it'll be shifted over 5 places. These 5 bits here get discarded, and they're replaced by zeros coming in here. So you can see the value in the destination register, which in this case is W6. And in this next example, we do an arithmetic shift, right? And this preserves the sign bit. So originally the sign bit was a 1, showing it was negative. And all the incoming bits then will also be ones showing that the overall result is also negative. Now we're doing a shift of 3. The 3 new bits come in, and they're all using the polarity of the previous sign bit. The rotate right instruction moves the bits from the right of the register and inserts them into the vacated bit positions on the left. This program will close up the shift and rotate instructions. We show the logical shift left instruction and logical shift right. We'll run 2 arithmetic shift rights. The second one will use the X register rather than the W registers that we've been using so far. Then we'll perform a rotate instruction to wrap things up. Finally run this through GDB, just to see everything in action. Our first task is to seed some of the registers, so we'll do a few moves here. Alright, so our first instruction is going to be logical shift left. Our destination register will be W5, and we're going to look at the contents of W1, and we're going to shift that 3 places. This is an immediate instruction. So if you look at W1 here, we have this value. We're actually going to shift this over 3 places. And you can do this by hand if you like, but 3 is represented in binary as 0011. And if we move that over 3 places, the new lowest 4 bits will be 1000, since the 1 is the original least significant bit, prior to the left shift, and the zeros are the new incoming bits. So again, it's probably easier just to draw out these bits, and spreadsheets are an ideal tool here. After that, then all the other bits will be repeating in 1001 all the way up. So after we execute that, we can see W5 has got the value that we discussed here. Look at W6 here. And you can see that the value is as we show in the comments. Now the arithmetic shift right instruction is interesting in the comments, and we need to pay a little bit of attention to it. If we look at the W2 register, we can see that because we're talking about a 32-bit W register here, that the high bit is set. So it's negative a 32-bit W register. So 8 is 1000 in binary. Now, when we execute this instruction, what will happen is that the incoming bits will be replaced by ones because we're replicating the negative bit. So originally, we had 1, 0, 0, 0 for 8, and then we're going to do a shift right. So we'll fill in with 1, 1, 1. That'll be our incoming bits. And then we have the 1, 0, 0, and so on. So if we look at W7, this is where we get our leading hex F from. The next instruction is going to be using 64-bit X registers. We're going to use X2. Well, X2's upper 32 bits are going to be 0, 0, 0, 0, all the way to the 8s in the lower 32-bit word. Originally, we only seeded the lower 32 bits. And then if we look at X0, that's got the value 5 of. Hit next. And look at register X9 in this case then, even though for a 32-bit, this was a negative number because the most significant bit was 1. But when this is extended out to a 64-bit X register, all these other bits are all 0, so the sign bit was positive. And that's why the result here is still positive. And then finally, we're going to execute the rotate instruction. We will use X3 as the destination, so that's the shift and rotate. We will be using these instructions extensively as we progress. One very common use for shifting is every time you shift a bit to the left, you're actually increasing it by a power of 2. So if you move it 2 places across, you're increasing it by 4, 3 places across 8, and so on. This is no different from decimal when we move our digits to the left, filling the incoming vacated space with a 0. It increases by a power of 10. When we do these kind of multiplications, we can simply implement register shift instructions, and often this is quicker. If you're just going to be multiplying by a number such as 2, 4, 8, a shift is usually the best way to go. So that's shift and rotate. And we'll finish that and move on to the next set of instructions. Next, we're going to look at logic operators. We will cover an exclusive OR. You may recall having done this at some previous stage, but a brief recap never hurts. We use truth tables to signify how these logical operators work. In the case of the AND function, if you look at the truth table here, the only way you'll get a true condition is if both inputs are true. So if A and B are true, then the output is true. Otherwise, it's false. Incidentally, the terms clear and false are used interchangeably for binary 0 and set and true for the binary 1 condition. With the OR truth table, you will get a true result if A or B is true. So here A is true. So the output is true. Here B is true, so the output is true. Here both are true, so the output is true. Now with exclusive OR, the function is exclusively to the OR condition. So if you look at this last result or condition, where both values are true, giving a true result, this condition is actually common with the AND table. So when both inputs are high, we get a high or true out, and with OR, the same thing happens. But with exclusive, OR, a true state is exclusive to the OR condition. So these two conditions here are not this one. So if A is 0 and B is 0, or A is false and B is false, then the output is false. If A is true or B is false, then the output is true. If A is false or B is true, then the output is true. But in the last line, this is not exclusive to the OR condition because it's also shared with AND, so in this case, it's 0. Now, the easiest way to remember it is if both inputs are the same, the output is a 0. And if the inputs are different, the output is a 1. So that's the truth table for these 3 operators. Next, we're going to do some bit twiddling, as we would term it. We can tell if a bit is a 1 or a 0 if we don't know by combining it with what we have termed a mask. And this is just a set of bits that we use together. So we'll use some rules here first of all. If we have a 1 and a value x, then the result is x. Since if the value was 0, 1 and 0 would give a 0 the same as x. And if it was a 1, 1 and 1 would give 1, which is also the same as x. Now if we are not interested in that bit, we can mask it with a 0 because we know anything ANDed with 0 is going to be 0. So it doesn't matter what x is, both conditions have to be true for the output to be true. So we can simply dispense with that bit by ANDing it with zeros. In the OR case, then if the value of one input is 0 or false, the output depends purely on the second one. So if this value here for x was 0, then the output would be 0. If this one was 1, the output would be 1 because 0 or 1 equals 1. 0 or 0 equals 0. And then if we look at 1 ORed with x, this will always be 1 because you'll need one of the conditions to be true to give the output true. So we don't care really what x is here. So here's some examples where we're using multiple bits. These are grouped into bytes. Now if you break down these bits, 55 hex would be 10101010, and we end it with hex 10100000, which is here. And if you simply AND the individual bits, you'll get this result here. So the other examples are shown as well. Little bit of shorthand, we may sometimes use the term IFF in the writings. This stands for if and only if. So we can certainly get rid of the bits we want by using these rules up here. Or we can set them to be a high value. And again, this will be our bit mask that we'll set up here. Now we need to talk a little bit about bitwise immediate, also known as logical immediate. You may recall when we did some move immediate instructions, we had a finite amount of bits that we could use with the constants. So we did some tricks like using LDR to load large data values from memory. We also used move keep to load the data in stages. With the logical immediate method, we have 3 immediate related fields. There's the N field, there's IMMR, and there's IMMS. So these 3 fields gives us 13 bits in total to make up an immediate value. Now this immediate value can be 64 bits in width with just a single instruction, and this is done by some very neat tricks. Now you're limited to the variety of patterns that you can use, but most of these patterns turn out to be quite useful anyway. And if you don't manage to get the desired constant using these patterns, then you can always use a constant from a register value instead. We're going to look at the mechanics of logical immediate in some detail. The IMMR holds rotation information, and we set the number of repeating bits in the IMMS field. And then we rotate these bits according to the value in IMMR. The ARM reference manual describes this under the explanation for AND immediate. This is fairly cryptic, so let's try and simplify things a little bit. It means there's repeated patterns of bits with varying sizes. So you could have a pattern like 0, 1, and that could be repeated the whole way through. Here the bits are grouped with an element size of 2. Another possibility is 0, 1, 1, 0, 0, 1, 1, 0, etc. 1, 1, which is a 4-bit pattern repeated 16 times. Here, the element size is 4. Now these patterns can be grouped in groups of 2 bits, 4 bits, 8 bits, 16 bits, or even a 64-bit pattern. Each of these patterns holds the same value. The register width divided by the element size corresponds to the number of patterns. The number of non-zero bits is the element size minus 1. So an 8-element pattern can hold up to 7 1-bits. A repeating pattern of 0, 1 then has the 1 in bit position 0 and can only go as far as 1 bit, since the value of the pattern size is 2 minus 1, which equals 1. A pattern size of 4 could have up to 3 1s. The tables signify this. The format of a logical instruction using a logical immediate could be AND immediate x0, x1 with the value of 0, 0, f, f, 0, 0, f, f, 0, 0, f, 0, 0, f, f. Now we're using a 64-bit value here. And of course, that can't be directly held within the fields of a 32-bit instruction. So what we do is we use the n, the IMMR bit value, and the IMM's fields to form this actual constant. We have 13 bits in total. The n makes up 1 bit, IMMR makes up 6 bits, and the IMMS is 6 bits as well. If you've got an element size of 64 bits, then really you only have one base pattern of 01, 01, 01, etc. But if we shifted the pattern over to the right, a rotation would change our pattern order to be 1, 0, 1, 0, 1, 0, etc. There are now 2 patterns, but only one base pattern, as the second is a derivative of it. This rotation is shown in the graphic. So if we have a 64-bit pattern, this will repeat just once. So a 32-bit pattern repeats twice. A 16-bit pattern will repeat 4 times. An 8-bit pattern will repeat 8 times. A 4-bit pattern repeats 16 times and a 2-bit pattern 32 times. So the number of bits in the pattern determines how often the pattern is repeated, and this corresponds to the size of the register. So for 64 bits divided by the element size, let's look at another pattern that we can get with an element size of 4. So we get a little bit more versatility with 4 and a wider range. Now if the element size is 4, then we can have either 1 bit, 2 bits, or 3 non-zero bits. So in other words, we could have a value of 1, a single 1 in the least significant place, 2 ones in the 2 least significant bits, and 3 ones in the 3 least significant bits. And these would be followed by a 0 in the most significant bit or bits depending on how many ones that you've selected. So, the 3 base patterns that we have are hex 777777, etc., hex 33333, etc., and hex 11111 recurring, etc. Now when we rotate each of these base patterns, we have a total of 4 possibilities. 1 base pattern, and the 3 rotations for each of the base patterns. So this gives us a total combination count of 12. The diagram shows the 3 base patterns, and then it shows the 9 rotated values. Let's look at a logical operator using a logical immediate. So in this first example, we're going to use the instruction AND x0 for the destination with x1 for the source. The immediate value is hex f0, 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 f0. Next, we isolate and identify the pattern, which is f0. We convert this pattern from hex to binary, so it's 11110000 repeated. So we can see that this is an 8-bit element size. The table shows that the first 3 most significant bits are encoded as 110. Specifying an 8-bit element. Then we look at the lower 3 bits, and these lower 3 bits represent the number of ones that are required less 1. So this is 4 minus 1, the value 3 in decimal, or 011 in binary. So the IMMS field will be 110011. The next stage is to position the non-zero bits in the right place. At the moment they are placed in the upper 4 bits, so we need to move them into the least significant 4 bits. This necessitates a shift of 4 places, so we need to do a 4-place rotation. This means our IMMR value will correspond to a value of 4 or 000100 in binary. The final encoded fields are n equal to 0, IMMS equal to 110011, and IMMR is 000100. Here is a second example showing encoding of logical immediate. This time we're going to use 16-bit elements. So you can see the repeated pattern is 00F, F, 00F, F, 00FF, and 00FF, so we require a total of 8 ones for the 2 Fs. This time we are dealing with a 16-bit element. Now the IMMS field will be 10011. The 3 least significant ones represent the number of non-zero bits, which is 8 minus 1. And then if we look at our table from earlier, we can see that the upper bit signifies a 16-bit element. Now in this case, the bits are placed where we want them, so we don't have to make any change to rotation. So here the IMMR field is 0. Sometimes we can't express the immediate bits that we need as a logical immediate. Well, there's a number of ways of working around this. The other form of AND is the register form, which is AND XD, XM, XN. So we can use the move keep instruction to load up a register, or we can use the LDR instruction to load data from memory. To load the bit values, you may find that this might be an easier way to do things, but if you can use logical immediate, you should, because it can have some performance benefits as well as using only a single instruction cycle, so we would recommend that. As an exercise, you should run this program. Make sure that it assembles correctly. It will not assemble correctly if you have values that can't be expressed. So this is something you could do and try. And then also you can do object dump. And then after running object dump, you can verify that the IMMR field and the IMMS field, as well as the N field, are what you expect them to be. So let's summarize logical immediate. Each of the patterns are identical. So if you have 8-bit elements, then each of those patterns will be repeated 8 times. They'll be identical. The first pattern that's shown is legal. The second one isn't, because you can see that there's a different pattern. There's 2 zeros in the second one, whereas there's only 1 0 between the ones in the first immediate. When we encode logical immediate, there are 3 fields. The N bit, which is a single bit field, IMMR, which specifies the rotation amount, and the IMMS, which is shown in the table below. The IMMS field specifies the number of ones in the pattern, as well as the element size. The only time the single bit N field is set to 1 is if you use an element size of 64 bits. The 6-bit IMMR field specifies the rotation amount. Now there are 6 bits available, so you can have 2 to the power of 6 or 0 to 63 rotations. 2 other forms of the AND instruction are shown here. We've already talked about the AND shifted register instructions. When a logical immediate bit field does not meet our needs, we can put the mask that we want into a register, and then we can simply AND these registers together. There is an optional shift as well that can be applied. The instruction format is shown there. The curly braces just signify that this part is optional. So if you don't need to do a shift, then you simply do an XD, XN, XM. The AND-S format is similar to the ADD-S instruction that we talked about earlier, near the beginning of this video tutorial. The instruction is used to set the flags, and they can also use a shift if you want. The next instruction to look at is the OR instruction. And the OR instruction, like the AND, can also use logical immediate. However, a major difference between OR and AND is that OR is used by the move bitmask immediate instruction. So move bitmask immediate is actually an alias of OR immediate. The instruction move XD immediate will assemble to or destination register, the 0 register, and the immediate. This will only happen though if the immediate conforms to these rules below. So it needs to be able to form a logical immediate. And we've discussed this previously. The source register is XZR for 64-bit or WZR if you're using 32-bit. And finally that there are no shift modifiers. The last logical instruction that we're going to discuss is exclusive OR. So again, nothing really new here. Exclusive OR instructions can be used as bitwise immediate or in shifted register forms. So we'll just wrap up with one more listing, and you can see that we've added in an exclusive OR instruction here. We've also included the rotate in it as well. The comments here show you the values, and if you want, you can assemble and run that, but we won't really dwell on that anymore. The last set of instructions that we're going to deal with relating to logical instructions is bit-twiddling, and this is typically where we start to fiddle around with individual bits and change them. So, the first one we're going to look at is bitwise clear, and the instruction with this is just simply BIC. And this can clear bits by executing the AND instruction with the inverse of the contents of an optionally shifted register. So the format is BIC destination register, XN, XM, and the shift in the amount. So the order is apply the shift to the XM register, invert the XM register, and then do the ANDing of XM with XN placing the result in RD. Next, we have bit field insert, BFI. And this instruction copies a set of bits from the least significant positions, which is specified in the width field of the source register, to a bit position that we also specify in the target register, and the bit field move is an alias for bit field move BFM. The next one is extract. With a 64-bit extract instruction extar, it combines two registers together so they look like a single 128-bit register. It will then right-shift the value over by the specified number of places in the instruction, and then it will return the lower 64 bits. So the format is EXTR, destination register, XMXN by the amount. The reverse instructions simply reverse the order of a register. Count leading zeros, CLZ will count the number of leading zeros in the register, so that's pretty straightforward. And then we have the test instruction, TST. This will check the polarity of an individual bit. The format is test RN bit pattern such as test X0. With the value 20, this will test bit 5, because if you look at bit 5, it's 001 00000 in binary of register X0. The 0 flag is set if the bit is clear or not set if the bit is set. The listing shown will first seed some of the registers and then move on to show examples of the bit-twiddling instructions that we have just discussed. So you can look through this. It's a good idea to work on these instructions with GDB or with a spreadsheet and verify that the instructions are giving the results that you expect, because some of these are reasonably complex. So it's a great way of testing your understanding. The listing shows the results in the comments. The steps are shown here, and you should be able to follow these without too much of an issue. And that's the end of our video at long last. So this has been one of the lengthier ones that lasted more than an hour. The next one will cover branching, functions, and macros. So once we've covered those, we can start getting into more serious programs where we can have loops and counters and all those good things that go into making up real useful programs. Thanks for your time.